So our next speaker is Nicolas Delfosse from Microsoft. He's going to tell us about beyond single-shot fault-tolerant error correction.
Thank you for the invitation. Thank you for giving me the opportunity to talk about this new work. It's a collaboration with Ben Reichard and Krista Zvory, and I'm going to talk about two papers, one from February and one that just appeared on the archive today. Our goal initially was to try to understand better fault tolerance, and with these two papers, we do two different things. The first one is a general study of fault tolerance, and the basic idea is pick a random fault tolerance scheme. What will be the cost of fault tolerance in that case? And we can expect that random fault tolerance scheme are pretty good because random codes are optimal. And the result is actually surprising. We were not expecting that, but what we prove is that we can do sub-single shot error correction. And the second paper that just appeared is it's a bunch of different techniques. It's many techniques. For a while, it was called just examples because it's 20, 30 different techniques that can be used to speed up error correction. And I'm going to talk about some of these techniques. So it's I don't know in which time zone you are, and it might be early for you. So I'm going to give you the take-home message right now, so that you can go back to bed if it's too late or too early. And the take-home message is that we can perform fault-tolerant error correction faster than you may imagine. And at least it's what surprised us. And it's actually even exponentially faster in some cases. So now I'm going to define the cost of fault tolerance. We consider an error correcting code. During the whole talk, I'm going to talk about linear codes or CSS codes. It applies to both, and in some cases, stabilizer codes. And we have a code defined by a set of parity checks, a set of measurements, and we will perform these measurements. If we want fault tolerance, we will have to measure a longer sequence, to implement a longer sequence of measurement. At least it's what we were expecting. And the cost, the overhead of fault tolerance will be the length of the fault tolerant sequence of measurement divided by the length of divided by the number of measurements that defines the code. And single shot means that the overhead is exactly 1. You measure exactly once all the stabilizer generators. In the case of surface code, for instance, you have an overhead that is d. You implement d cube measurements, and you have of the order of d square independent constraints, independent measurements. In the case of gauge color codes, which is the original idea of single shot, it's where Hector Bombin introduced the term single shot. We have a constant overhead. I say constant and not exactly 1. So with this definition, the overhead it's not single shot with this definition, because you measure gauge operator and you can have more gauge operators than stabilizers, but it's a constant. And with LDPC code, such as shields, hypergraph product codes, we can have a constant overhead. And in the general case, if we use, for instance, shore error correction or flag error correction, we will have an overhead that is of order d square. It's actually very expensive. And we will improve this cost for a general code. We'll lower it to a logarithmic cost. And using this result, we'll prove that in some cases, we can have an overhead that is strictly smaller than 1. It's what I mean by unexpected. We can actually perform fault tolerance for cheaper than error correction itself. it seems counterintuitive that fault-tolerant error correction can be cheaper than error correction. But it's not incorrect. And it's like it can actually be exponentially cheaper, exponentially faster. So I'm going to talk about fault-tolerant first. I'm going to come back to the definition of fault tolerance. Then I'm going to explain how we can prove the existence of sub-single-shot sequences. And finally, I'm going to come back to explicit constructions with single-shot error correction and single-shot logical operations. So first, fault tolerance. What do I mean by fault tolerance? We consider an error correcting code. So in this case, you consider the repetition code where each bit is repeated 3 times. So you have a 3-bit 111 repeated to encode a single bit. And you will implement parity check measurements to check the parity of those pairs of bits. They are supposed to be identical. So the first parity gives you 0 in the first case. And the second parity is supposed to give you 0, but it's flipped. There is a fault, and it's going to give you 1. If there is a fault, the syndrome is incorrect. And when you try to correct, you will inject an additional error on the data. So this is the consequence of a faulty syndrome, a syndrome bit flip. It's the first type of fault. And the second type of fault that may occur is an internal bit flip. So during a measurement or after a measurement, or a waiting bit can be flipped during the scheme. So error correction itself is noisy. And the effect of that is that the syndrome is going to be partially incorrect. If an error occurs after a measurement, it's not detected by the measurement when it should be. So the syndrome is incorrect, and we will have additional errors by correcting. And the solution is use more measurements. Now, how do we define fault tolerance? So for that, we can go back to Gottesman, and here we took a variant of Gottesman definition. It's almost the same. It's only a slight simplification, and we can make this simplification because Gottesman's definition was used for concatenation. Here we are not going to use concatenation. We are simply going to use one fixed error correcting code or a family of linear code. But we don't need the condition related to concatenation. It's going to simplify. It's going to make everything simpler. And the condition is that the number of residual errors, the number of bit flips that remain after error correction, must be smaller than the number of internal faults. And by internal fault, I mean either internal bit flip on the data or bit flip on the syndrome. So if you have this condition, you have fault tolerance. It's basically the first condition of Gottesman. And why is that a good notion of fault tolerance? Because in this setting, if you have fault tolerance, you can consider this model where you store data and you keep running error correction at regular time interval to recover your data and to protect your data. And if you do that, when you start with a fault rate P, you end up with encoded data with a fault rate, which is of the order of P to the D minus 1/2. This is exactly the order we want to achieve with a code of minimum distance D. So even in the presence of fault, we can achieve the same order as error correction. And it works because we will correct input errors. We will correct errors that occur before the error correction cycle. And internal fault will be moved to the next stage and corrected by the next round of error correction. And we can prove that based on it's applying the rectangle method from Aliferis, Gottesman, and Presker. It's a simplified version, but the same argument. So it's a good definition of fault tolerance. Now, what is the most common fault tolerant scheme? It's sure error correction. And how does it work? You want to use the syndrome, but you cannot trust it. Some bits may be flipped. So you will repeat the standard measurement. For instance, in this case, there is you repeat 4 times, and during the second standard measurement, you have a bit flip in the syndrome. So your 2 first syndrome are not identical. The third syndrome is not equal to the previous one, so you will not use it, you cannot trust it. And the fourth syndrome will be identical to the third one. Now that you have 2 identical syndrome, you can trust them and you can correct. It works for any code, so it's very general, but it's very expensive. It requires of an overhead of order d square. You need to repeat this up to d square the syndrome measurements. And we can do better. So here I show you an example where for the same code, for Steen code or Hamming code, we have a sequence with only 5 measurements instead of 12. And with 5 measurements, we can check numerically or by hand that any single input error can be corrected. Any errors that occur before the cycle can be corrected, even and cannot be confused with an internal fault. Now I'm going to generalize this example to asymptotically large sequences and show you that and tell you why we can perform sub-single shot error correction. So the proof goes in 2 steps. The general idea goes in 2 steps. First, I want to give you some intuition why we can correct syndrome bits, assuming there is no internal errors, internal bit flip on the data. And then we will move to a different idea to correct simultaneously, a slightly different idea to correct simultaneously internal bit flip on the data and syndrome bit flip. So this idea is appeared, as far as I know, the first time it appeared was with Fujiwara, and it was used later with Ashik Min and collaborators, with Earl last year, with LDPC codes, and with Zheng and collaborators with convolutional codes. So the idea is very simple. You cannot trust the syndrome, then encode it. And what Short does is repeating the syndrome measurement. It's just using a repetition code. Instead of that, you can use a better code than the repetition code. So you have 3 syndrome bits. You can encode it with a linear code with distance 3. So it's going to encode the 3 syndrome bits into 6 bits. The 3 syndrome bits, 6 bits. And any single bit flip in the syndrome can be corrected using this code, this encoding of the syndrome. So now you decode in 2 steps. First, you correct the syndrome. Then you use this syndrome, this corrected syndrome, to correct the data. And here you have 6 measurements. This kind of scheme works, but this 2-step decoder is not optimal. We can do both of them simultaneously. So instead of that, we can correct the syndrome and the syndrome bits and the data simultaneously. And it allows us to do a little bit better. We can combine the performance of both codes. For instance, we can encode the syndrome with a code with distance 2. So we encode the 3 syndrome bits into only 5 bits. And we show that only 5 measurements are enough, even if the encoding of the syndrome does not allow for correction of 1 bit flip by itself. So correcting together does a little bit better. And now, what about internal bit flip? So the previous idea works only when there is no internal bit flip. In the case of internal bit flip, we have an issue. And the basic idea is that if an internal fault appears too late, we don't have enough information about this fault to correct it. It's only detected by the last few measurements. And in the extreme case, if an internal fault appears after the last measurement, it's not detected at all by anything. There is no information about this fault. We cannot expect to correct that. So let's use this idea and define a region of early fault, early bit flip, early internal errors that we will correct, and late errors that we will ignore and let go through the next error correction cycle. And if we do that, we can define a decoder that does that. We identify early errors and late error in a technical way. I'm not going to go through the detail, but basically once we have a region defining what is early, we have early faults that will be corrected by our decoder, late fault like the red region that appear in the latest measurement that will be ignored by the decoder, and some partially corrected fault that appear in the middle of the scheme. And we design the sequence, the decoder and the sequence in such a way that we cannot have an input errors that crosses the boundary of the early region. So that if an input error appears, the whole error and all the faults that are connected and related to this input error will be corrected. And once we have this decoder, the argument becomes simple. We just pick a random sequence. We prove that this decoder, this truncated decoder, works with high probability, and it corrects all the faults that we need to correct for fault tolerance. So we can prove that we have fault tolerance with a random sequence. Then we look at the length of this sequence, and we obtain these two results. If we have a polynomial minimum distance, we need only d log d measurements for fault tolerance. And if we have a polylog minimum distance, we need d to the some power of d measurements. And you can note that it doesn't depend on n. The length of the sequence is independent of n. So if you take a polynomial minimum distance, which is square root of n, for instance, then you get a sub-single shot sequence. You get a sequence whose length is smaller than the number of measurements defining the code. And in the case of polylog minimum distance, you get a sequence that is exponentially smaller. To give you a better idea of what I mean by early faults and late faults, here is a set of early fault and late faults. So the top, the red region, are the set of bit flips that are early enough so that they can be corrected. And the green region are the problematic faults. Maybe it should be red. So the green region appear too late to be corrected. You can see, for instance, that the last row of bit flips cannot be corrected. But even some that trigger only one syndrome bit cannot be corrected and should not be corrected. If you try to correct them, you will do more harm than good. So now, as I was telling you, it seems counterintuitive. It seems too good to be true. So is it too good to be true? And we went to the proof multiple times, and we were convinced that it works. So I started using Twitter recently, and it's a good way to get some fast feedback about your result. And the first feedback I got was this one. So I guess I'm not the only one thinking that it's too good to be true. But let me try to convince you that there is actually a reason why. We can intuitively understand why sub-single shot is possible. And the deep reason why is that we are using bad codes. If we are considering codes such as the surface code or all non-LDPC codes that have a polynomial distance, just like we just saw with Gilles' talk, if the distance is polynomial, it's a bad code. It's a sublinear distance. And in that case, we can pick a random code that is better. So we will pick a random code C prime that contains our code and with the same distance, but with a larger number of logical qubits. or logical bits. It works for linear or quantum codes. Now that we have a larger code that contains our code, we can run fault-tolerant error correction with the larger code, and it's going to correct the subcode. And the thing is that the larger code has fewer measurements. It's defined by fewer parity checks because it's larger. So you can expect fault tolerance with a smaller number of measurements, with fewer measurements. And that means sub-single shot exists because we are using bad codes. And if we use very bad codes with a logarithmic minimum distance, with a polylog distance, then we have exponentially faster sub-single shot fault tolerance. So it makes.
Can I interrupt with a question, Nicola?
Sure.
How do you know that the distance didn't go down when you grow the code like this?
So I know it because I'm not telling you it's true for all codes. I'm telling you we will build a code that satisfies that. And how do we know that? Because we will pick a random code. If we pick a random code, the distance is going to be linear. And
okay.
That's the reason why. Yeah. But it's true. We need a larger distance. Thanks for clarifying. So now I'm going to move to explicit construction. We are convinced we have an existential argument for very fast fault-tolerant scheme. Can we make it practical? Can we make it more concrete? And this is our very new work. So first, I'm going to come back to STIN code. And in the case of STIN, I'm going to use a different notation now that you are familiar with this sequence of measurements. I'm not going to add circles for fault. I'm just going to show you the measurements. So the measurements are a pink square for Z measurements and blue for X measurements. And the last one will be Y. So now if you perform Shor error correction, you need 24 measurements and the overhead is 4. If you perform the scheme I showed before with only 5 measurements, you can correct with 5 measurements in X and 5 measurements in Z. So in 10 measurements, you can perform fault-tolerant error correction. But you can do a little bit better. Here you measure only X and Z, but if you introduce Y measurements, you can do that in only 8 measurements. And you can do even better if you have the ability to measure general Pauli operators, not only X, Y, or Z, but a mixture of the 3. And then you need only 7 measurements. And we are down there. We don't know if it's possible to, I think we know that it's not possible to do it with 6 measurements. So it cannot be single shot with this code, but it's almost single shot. And the speed up over Shor is clear. Now, can we do a little bit better? And for that, we design codes.
Can I interrupt again? Because there's 2 questions from the audience that I think are pretty short. So before you move to the next slide. So Andrew Landau asks, in your definition of the overhead, the denominator is defined as the number of measurements defining the code. Should the code include the syndrome qubits, which are now encoded too?
It will be a fair definition of fault tolerant. It's not the one we take. Our goal is to speed up error correction. So in that sense, the overhead for measurement is necessary. It is there. And we assume something like a cat state to implement each measurement. But we look at the overhead in time.
Okay. And that actually, I think, ties in nicely to the next question, which is Anand Ganti, who asks, it seems like the weight of the checks is not factoring into the cost at all. Is it true that in this scheme, there is no bound on the weight of the checks?
That's true. We do not consider the weight here.
Okay, thanks.
So yeah, it's the most simple definition you can come up with. So now, let's pick a different code. The STIN code is not good enough for fault tolerance. We'll pick a different code. We'll pick the extended Hamming code. And with this code, we have a sequence that requires exactly 10 measurements for 10 stabilizers, for 10 measurements defining the code. So the overhead is exactly 1. It's actually quite surprising. We don't need any extra measurement to perform fault tolerance. We can just measure this exact set of stabilizer in that order. So it's satisfying. It's optimal in some sense. And now let's do a little bit better. We have single shot error correction, but we will need to implement logical operation. So we looked at logical measurements. And if you want to implement logical measurements, you have 3 choices. First, you can do the same thing that you do for any CSS code or for the surface code. You just destroy your block. You measure all the qubits in the computational basis, and you post-process this data. It's going to give you the value of all the logical operator. But you cannot measure one of the logical operator, or you cannot measure an operator like Z1, Z5 in our block of 6 logical qubits. You will destroy everything. So after that, there is a huge cost. You have to re-prepare everything. And you might lose the whole computation you have done on the qubits you don't want to measure. The alternative is teleport your data, the data you want to measure, teleport the logical qubit in another block, and destroy this other block. There is a cost, is that you need to prepare another block, test it, and destroy it, and run the teleportation. And the third strategy is to use Shor. So I'm going to pick a representative of my logical operator. I'm going to measure it. And then I'm going to run error correction, measure it again, and run error correction, measure it again. And I'm going to extract the logical outcome like that, without destroying. For instance, it's this scheme for the 16-qubit extended Hamming code. So for our 16-qubit code, we measure the logical operator. It's the first row here. It's one of the logical operator of the code. And we run X error correction to correct the X fault, because X fault might flip the outcome of the next logical measurement. So we remove X fault, we run again the logical measurement, and we keep going. And at the end, we need to run the correction of Z errors. And the total number of measurements you need is pretty large, when in principle, the only thing you want to extract is one logical measurement. So you need one measurement, and you need also a round of error correction. So in principle, the number of measurements you need for a single shot logical measurement should be the number of stabilizer generator plus 1, because we want to extract one logical measurement. And we can do that. We can do that with this sequence. So the idea is to take four non-overlapping stabilizers, non-overlapping representative of the logical, and you measure these 4, combine with some Z measurement, and this combination will allow you to do 2 things simultaneously. First, you can extract the logical measurement, and second, you can run X error correction with using the outcome of the logical measurement. And by doing that, you get a sequence of exactly 11 measurements to run error correction plus 1 logical measurement. So this is again single shot. This is an overhead of 1. And now we have, so I showed you one example of a sequence of single shot logical measurements, but we can actually implement all X measurement and all Z measurement in the same way. We don't have one sequence, we have 2 of them. And with that, we can reach all the logical measurements, including, for instance, Z1, Z5, Z6, by permuting this sequence, permuting the qubits in this sequence. So we don't need to physically permute the qubit, we just measure a permutation of this sequence. And by doing that, we need one sequence for fault tolerance, which is always the same, and the permutation of these two logical sequences allow you to reach any Z logical measurements. And by swapping X and Z, you get all the X logical measurements. So we have a code, this extended Hamming code, that has a very particular structure and that allows us to do fault-tolerant error correction in single shot, but also fault-tolerant logical measurement in single shot. And so this is my last slide. I want to point out that in this paper, we also added 10 open problems. 10 open problems that are motivated by the study of this paper. So we go through Hamming code, or general distance streak code, or the effect of puncturing, cyclic code, Reed-Muller codes, and topological codes, and similar question for logical measurement and logical operations. And we believe that this question can help us to improve further fault tolerance and to speed up fault tolerance for general codes. I can go through some of these open problems if you guys are interested. And otherwise, my conclusion is that we can do fault tolerance with a very short sequence for general codes. We can actually do sub-single shot and exponentially fast sub-single shot. And we design explicit sequences for some codes and explicit sequences for single shot logical measurement. And we can go further. So the conjecture is incorrect here. I'm sorry about that. So this is what we proved. Fault-tolerant error correction is possible with d log d measurements. What we conjecture is that we can remove the factor log. We can run fault tolerance with only d measurement of order d measurements. We cannot prove it, and it seems that the issue is the decoder that we design. And maybe the notion of minimum distance. We consider a notion of minimum distance that we call the circuit distance. Maybe there is a better notion and a better decoder that will allow us to do better than d log d. Then we didn't show any explicit sequences for sub-single shot error correction because we prove the existence asymptotically and we study explicit sequences for small distance code. It would be interesting to show some explicit constructions. And so one last comment, because I know that Marcus or Ben are gonna ask me about that. So yesterday we saw non-Clifford gate, single shot non-Clifford gate in some sense for one specific type of code, for gauge color code. So how does it compare? It's not exactly comparable. The reason is that if you consider gauge color code, you consider a specific code and a code that is bad in the sense that it encodes only one logical qubit into a very large number of physical qubits. It has, of course, some advantages, but it's a specific construction. And here we have the advantage of using multiple logical qubits in the same block. So we can perform a multi-qubit logical operation in single shot. So it's not exactly comparable, but those two techniques might be complementary, and we didn't explore non-Clifford gates. So I'm going to finish with a picture from our paper where we compare the code rate and the time required for fault tolerance. Thank you.
Thank you, Nicolas, for a wonderful talk. We have time for some questions. I see two. So the first question is Daniel Gottesman. I think, Daniel, you can, I can ask for you, or you can unmute yourself. Why don't you ask your question, Daniel?
Yeah, so I wanted to know how to compare this scheme to Steen and nil error correction. I mean, you know, Steen error correction really only uses just 2 measurements, and nil error correction just 1 measurement. The ancillas that are more complicated, but you need very large cat states, which are vulnerable to phase errors. So how do you decide which one is better?
So we did not compare, that's true. And the reason is that STEAN has the cost of preparing an ancilla that I believe is much more expensive than cat state. We didn't compare.
A large cat state, if you just get one phase error, then it's the wrong answer. So that's kind of different from the regime that you were thinking of, where the error rate per synchrome bit is constant, right?
I mean, if we get one phase error, it's going to be transformed into a syndrome bit flip that we can correct with our scheme.
Well, not if the error rate is too high, right? If it's very, very high synchrome bit error rate, because the cat states are large, that's going to be a problem.
Yeah, if the cat state is, I mean, asymptotically, it's going to require something else. For the code we consider here that are reasonable lengths, it remains reasonable. Yes, and asymptotically, STEAN also has some issues. It's non-trivial to prepare this large ancilla and to test it and to make sure that the ancilla is good up to correction of D over 2 faults. So I think there is a similar issue in both cases, but I don't know exactly how they compare numerically.
Okay.
And our next question is Thomas Joachim O'Connor, who asks, do you think your methods could be adapted to measure non-Pauli logical observables, such as Hadamard, which could be useful for magic state distillation?
Yeah, that's a good idea. I don't know. I don't see any. I mean, in principle, the idea of optimizing the length of measurement sequences applies also to distillation. That's true, and also to non-Clifford gates. The propagation of faults through non-Pauli measurement might be more complicated to study, and here we still don't have a very good understanding of large distance single shot sequences or short sequences. So it's already non-trivial for our Pauli errors, for our Pauli measurements. It might be more difficult for non-Pauli, but it could be useful. Yeah.
Are there any other questions for Nicolas?
I have a quick question, actually. So maybe also half an observation. So I think when Daniel was asking his question, he was asking about error rates. I wonder if part of the confusion in that conversation there was, are you mostly talking about adversarial errors? So you're talking about fault tolerance. So how many faults can you tolerate in such a way that there's a certain amount of residual error? But you don't necessarily have a threshold, right? In the sense of
So in the case of a fixed block code, I guess the question does not really apply. We have a pseudo threshold for each of them. It might be low, it might be higher for some codes. And what we believe, and one of our motivation is, the faster the sequence, the higher the pseudo threshold and the better the performance. In the case of asymptotic sub-single shot sequences, we don't prove that there is a threshold, and we don't introduce we don't study the threshold. So that's right, and there is still a lot of open question in that regime.
Thanks.
Yeah, just following on, I guess that would also depend on the weight of the stabilizer generators that you're measuring.
Yes, well. It depends on the weight.
Yeah,
that's true.
But I thought you said that you choose the syndrome code randomly. So if you start off with a code where the stabilizers have constant weights, then after you've done this randomization process, they'll be, with high probability, there'll be high weight.
Yes, by having shorter sequences, sometimes you will increase the weight. And in the random case of the proof, you typically have large weight. Yes.
Yeah. So this is the thing that I'm curious about. Is it possible that you can have a code that if you measured the stabilizer generators would have a threshold, but when you do this sub-Singleshot thing where you randomly choose kind of products of stabilizers, whether you have some problems because you've kind of lost the LDPC property, even though it's kind of hidden there in the generator.
Yeah, that's true. There is a regime in the LDPC regime. You already have good stabilizer generators. You should keep them. That's right. Maybe one solution to improve our argument and to make it work for LDPC code is to introduce the number of rounds of measurement instead of the number of measurement needed as an overhead. So it gives you a different notion. And by introducing parallelism, it's gonna by counting the overhead like that, it's gonna encourage you to introduce parallelism, which means low weight measurements. So that might help, but it's not what we studied. It could be useful, that's true.
Okay, I think that's all. We're a bit over time, and so let's thank both Nicolas and Gilles for their wonderful talks. I think we may have the only announcement I can think of is check out the Slack channel where hopefully Nicolas and Gilles can log on and answer further questions or discuss about their work.